In this module, we're going to talk about another theory of bonding called molecular orbital theory. Now, you may ask, why so many theories? Well, the ones we've talked about so far, basically Lewis theory, valence bond theory, and hybridization theory, did a good job of doing what they did. But we run across experimental data that doesn't match up with theory. Theory always loses. We have to come up with another theory or modify that theory. In this case, we came up with molecular orbital theory. And one of the experiments that led us to do this is that oxygen, the molecule O2, it's in fact paramagnetic. Okay, so some definitions for you. Paramagnetic means that there's at least one unpaired electron in the molecule somewhere. Diamagnetic means that all the electrons are paired up. There's always one spin up, one spin down in every single orbital. And what the effect of this is that if there's an electron that doesn't have another electron in the same orbital with it that has the opposite spin, that one electron acts itself like a little magnet. And that makes the whole molecule act like a magnet. And what does that mean, to act like a magnet? Well, one of the things that magnets do is when you put them next to another magnet, they're either attracted or repelled, depending upon which pole they come close to. And in fact, this picture right here shows that quite clearly. This is a magnet right here, an electromagnet, and this is liquid oxygen being poured through here, and it's trapped, it's held, it's attracted to the two poles in the magnet. This is liquid nitrogen, which is diamagnetic, and when you pour it through the same magnet, it just goes right on through. So in fact, we know experimentally that oxygen is paramagnetic. There's the Lewis structure for it. All the electrons are paired up. That would make it seem to be diamagnetic. Same thing when you do hybridization theory, everything is paired up. So, time for another theory, molecular orbital theory. What we do in molecular orbital theory basically is we take the valence orbitals in all of the atoms in the molecule and mix them together to form what we call molecular orbitals. This is similar to hybridization theory. See, the difference is in hybridization theory, we only mixed together the atomic orbitals on a single atom, an s and 3 p's or something like that on like a carbon atom. Now here what we're doing is we're taking valence orbitals from all over the whole molecule, mixing them together and making orbitals that can spread out over the entire molecule rather than being localized on a single atom. Call these molecular orbitals. Now we'll start with hydrogen. Pretty simple. There's only two atoms. There's only the 1s orbital here and the 1s orbital here. And another thing about combining orbitals, just like in hybridization theory, however many we start with, we always have to make that many. So we're going to start with a 1s orbital from here and 1s orbital from here, and we're going to get two molecular orbitals. These are what they look like. And notice that in one of these, the orbital itself, that is where the electrons can be, is concentrated between the two nuclei. In the other, it's spread out on the outsides of the nuclei. We call this a bonding molecular orbital because it lowers the energy of the molecule compared to them being separate, the atoms. This, we call something like this an anti-bonding molecular orbital, and that is because the energy is higher here than it is for the separate atoms, because the nuclei are more exposed to each other and they repel each other more strongly than over here. So if we combine all those together, we take two hydrogen atoms, make a molecular orbital, we get a bonding and an anti-bonding molecular orbital. These two are just one orbital, the anti-bonding. In terms of energy diagrams, it looks like this. So this is the 1s orbital on one hydrogen atom. This is the 1s orbital on the other hydrogen atom. When we mix them together, we make a bonding molecular orbital. We call this a sigma 1s. And an anti-bonding molecular orbital, we call this a sigma star 1s. The star or the asterisk means anti-bonding, and notice energy is right here. This molecular orbital is higher in energy than these atomic orbitals, but this one's lower. So it's good for electrons to be in bonding molecular orbitals, and it's bad or high energy for them to be in anti-bonding molecular orbitals. And so what we do is we do the same thing as we did with electron configurations. Basically, however many valence electrons we have, we just put them into the molecular orbitals. So we had one valence electron from this atom and one from this, two valence electrons. We can put 2 electrons at most into each molecular orbital, just like regular atomic orbitals. And if they're in the same orbital, they have to have opposite spins. So 2 electrons in here, none in here. Now let's look at the helium molecule, if there were such a thing, He2. And we can do the same sort of thing. The difference here is that we have 2 electrons coming from each atom, so when we start putting them into the molecular orbitals, we put 2 guys in here, there's still 2 other valence electrons left. They have to go up in here. Now, what does that mean? Well, now we get to what's called bond order. We can calculate real easily from a molecular orbital energy level diagram. That's what this is called, a molecular orbital energy level diagram. We can calculate what's called the bond order. And this is how you do it. It's real simple. Just count up how many bonding electrons there are, electrons in bonding molecular orbitals, and subtract out how many electrons are in anti-bonding molecular orbitals, the ones with the stars. Take the difference, divide by 2, and that's the bond order. If we do that for hydrogen, we get 2 electrons in this bonding orbital, 0 in the anti-bonding. 2 minus 0 over 2 is 1. Helium, dihelium, we get 2 minus 2 over 2 is 0. What does that tell us? Well, a bond order of 0 says that molecular orbital theory predicts that molecule will not exist in nature. And in fact, this molecule does not exist in nature. If we get anything other than 0, it'll never be negative, it'll be positive. That means that molecular orbital theory predicts that it's possible for that molecule to exist. And the bond order tells us something. We'll see that in just a minute. But the bond order of 1 for hydrogen predicts that this molecule exists, and this means that it's basically a single bond and some other things. So memorize how to calculate bond order. That's real easy. Now, once we get past the first row of the periodic table, we're not going to go past the second row, by the way. Get into the second row with lithium. We still have the 1s electrons. They're not valence electrons anymore, so we don't really write them down. We still have the sigma 1s and the sigma star 1s down here, these guys, but they're both full, just like this, and effectively they cancel each other out, so we don't even bother writing them. When we're doing the molecular orbital energy level diagrams for the second row elements, we just start with the 2s atomic orbitals, combine them to make sigma 2s, a bonding molecular orbital for 2s, and an antibonding sigma star 2s, which are higher in energy than the 1s, but the 1s are full, so we ignore them. And once we get to the p orbitals, I do something a little bit differently. They combine like this. We have 3 p orbitals from here and 3 p orbitals from here. This is B2, diboron. Notice, okay, let's go back and look at lithium for a second. What can we say about it? Well, each lithium has 1 valence electron. Make sure you know how you know that. And so we take 1 from here, combining, put 2 into here. So our bond order, check this, it should be 1. And that means it's predicted to exist. And bond order of 1. And also it's diamagnetic. That's an important thing too. Now, let's go to the boron molecule, B2. Here's what we would expect if we were to take 3 2p orbitals from each atom and mix them together. We'd expect, we'd expect a sigma 2p bonding molecular orbital, 2 what we call pi 2p bonding orbitals, and then 2 pi 2p anti-bonding, and a sigma 2p anti-bonding. Difference between sigma and pi bonding and anti-bonding molecular orbitals. Sigma, it's just like we defined previously with hybridization theory. It's head-on overlap, and pi is like sideways overlap. And so with bonding and anti-bonding. Now, if this were the case, boron has 2s2, 2p1 for its valence electrons. The 2s and 2s from each go into here and here. The 2p1 here and here goes down here. And that would give us a bond order of 2 plus 2 is 4 minus 2 is 1. That's okay. But it also predicts that this molecule would be diamagnetic. Now it ends up that we know experimentally this molecule is paramagnetic. And what's happening here is that when s and p orbitals are close in energy, they what we call mix. And it flips. The only effect that you guys really care about here is that it flips the order of these two, sigma 2p and pi 2p. It's instead of having the sigma 2p on the bottom, pi 2p is on the bottom. And so when we take the electrons and we add them into the molecular orbitals here, we still get the same bond order, 2 plus 2 is 4 minus 2 is 2 divided by 2 is 1. So a bond order of 1. But now we get this being paramagnetic. And this is the actual molecular orbital energy level diagram for this molecule right here. So we have two molecular orbital energy level diagrams for the second row diatomic elements. And that's as far as we're really going with this. One looks like this. This is sigma 2s, sigma star 2s, then the pi 2p's are down here, then comes a sigma 2p, pi star 2p's, and sigma star 2p's. This is for when there is 2s, 2p mixing, and you use these for the diatomic element molecules, the second row from lithium through nitrogen, and also for the heteronuclear diatomic nitrogen monoxide. This is what you use for that. This one here, this is with no mixing, so the sigma 2p comes before the pi 2p. This is the only difference, these blue ones here. Their orders. Everything else is the same. Use this for second row diatomics where it's oxygen, fluorine, neon, or if it's two elements from the second row that are not next to each other in the periodic table, then you use this one because there's no mixing. So let's see how we use these. Memorize these, by the way. This is real important. So let's say we have this molecule, oxygen monofluoride, and we want to know the bond order. We could also tell whether it's paramagnetic or diamagnetic. So the first thing you're going to want to do is count up the valence electrons. Oxygen has 6, fluorine has 7, so that's 13 valence electrons. The next, which of these do we use? The one with mixing or without mixing? Well, oxygen and fluorine means we use the one without mixing, so we're going to use this one right here. And all we do here is we put in the 13 valence electrons following the same rules we did with electron configurations. So one, oops, that's not going to show up. There we go. 1, 2, opposite spins in the same orbital, 3, 4, 5, 6, and then Hund's rule, 1 in each first with the same spin, 7, 8. Then we pair them up, 9, 10, 11, 12, 13. Now we're done. So now we can see that the bond order is going to be 2, 4, 6, 8 valence electrons minus, valence bonding electrons minus 2, 4, 5 anti-bonding electrons. You see where they're coming from? Divided by 2 equals 3/2 or 1.5. And it's perfectly fine to have non-integer bond orders. That ends up meaning that it's between a single bond and a double bond in terms of length and strength. All right, so here's what bond order means. It's related to the length and strength of a bond. The higher the bond order is, the shorter and stronger the bond. You should know this stuff. If we have a bond order of 1, it's roughly a single bond. Bond order of 2, roughly a double bond. And bond order of 3, roughly a triple bond. Now, if we have a bond order between two integers, that means it's, in terms of length and strength, it's between the two. Now, last thing we need to talk about here is something you won't really have to do, but it's good to understand what's happening with it. Is you can combine hybridization theory and molecular orbital theory, and we do this with benzene to explain its extraordinary stability. So if we look at benzene, benzene is C6H6. That's the formula. And it's a ring. The 6 carbons are in a ring, and each carbon has a hydrogen attached to it with a single bond, sigma bond. And there are alternating single and double bonds. So each carbon is sp2 hybridized. And so what we do, we use hybridization theory to make what we call the sigma network. The sigma bonds are the sp2 from each carbon overlapping and an sp2 from a carbon with a hydrogen, and so on, making a ring. And then we take the unhybridized p orbitals on each of the 6 carbon atoms, 1 from each, and we mix them together in a molecular orbital, and we get 6 molecular orbitals. And this is what one of those orbitals looks like. And what that shows us is that those electrons, the 2 electrons would be in here. There's 5 other molecular orbitals that look similar to this. They're spread out over the whole molecule. This is what we call delocalization, and it's a stabilizing factor. This is related to the resonance forms that we would get.